Welcome to video 22 on the TTB course. This video is from part 5 of the TTB course. In part 5 we first introduce a set of TT platforms. We then illustrate how these platforms can be applied using a range of case studies. In this video we consider in outline the development of part of a safety-related industrial monitoring system, or IMS. The material in this video is from Chapter 2 in the ERES2 book. This video just provides a summary of the material that's presented in much more detail in the book itself, and the video will make very little sense if you haven't read the book chapter. If you haven't read the book yet, I suggest you read Chapter 22 first and then watch this video again. So in this case study, we're concerned with the development of a sounder unit. We'll simply call it the sounder for use as part of an industrial monitoring system. So this unit involves controlling this horn unit that's illustrated here, controlling a horn unit like this in order to sound an alarm if a fire, a gas leak or another potential hazard is detected by the IMS. So this is what the whole IMS looks like. We're not concerned with the whole IMS in this study, but it's important to understand the bigger picture. So we have multiple sensors. For example, these are gas sensors, these are heat sensors, these are smoke detectors, etc., that are intended to be used as part of this monitoring system to pick up, for example, chemical leaks, etc., in this plant. So there will be numerous different sensors. In this design, we assume that each sensor is connected to a dedicated CAN bus and connects to the IMS controller. The IMS controller is the brains of the unit. It takes the information from the sensors, it takes and feeds this information, if required, to sound the alarm by means of these sounder units, which are basically required to control a high volume horn, and by means of these beacon units. So the beacons basically turn on flash high intensity lights. There's lots of CAN buses involved. The IMS controller is responsible for receiving information from the sensors and receiving status information from the sounder units and from the beacon units, and it makes all the decisions based on the information that it receives. As we've noted, we're not concerned with the whole system here. We're only concerned with the sounder unit. So the sounder unit talks to the IMS controller and sends status messages back to the IMS controller. Its fundamental job, though, is to control the sounder itself and to receive feedback from the sounder. So basically it checks, it's supposed to turn on this horn and then be sure that once it's turned on the horn, that the horn has actually been activated. And that's the simple job that's the responsibility of this sounder unit. However, if the sounder unit doesn't work, people may be injured or even killed in this kind of setting. So this simple functionality must be carried out very carefully, and we must be sure that if a message comes in and says sound the alarm, that this sounder unit will achieve that. So we've identified the following functional safety requirements for the sounder. So functional safety requirement 1. The sounder shall activate its horn when it receives a valid activate sounder command from the controller unit. This is clearly a key safety requirement. Functional safety requirement 2. After activating its horn in compliance with FSR 1, the sounder unit shall keep the horn activated for the period of time specified in seconds in the activate sounder command, unless until it receives a deactivate sounder command from the controller. Again, this is a key safety requirement. Functional safety requirement 3. The sounder shall disable the horn if it enters a fault state. This is clearly an important safety requirement. If we keep getting false alarms from our sounder unit, then we'll have much less faith. When we get a real alarm, we may not believe that it's valid, and again, this may have dangerous consequences. So it's important that the alarm is sounded when the sounder receives a command from the controller telling it to sound the alarm. It's important that the alarm sounds for the correct period of time, and it's important that the alarm does not go off when it's not intended to go off. These are all important safety considerations. So our focus here is on identifying an appropriate platform to implement this design. So we are told, and you can read more about this in the book chapter, we're told that this is to be a SIL 2 design. So it's a SIL 2 design developed in compliance with IEC 61508. So this, based on the table that's presented in Appendix 3 of the ERES2 book, gives us some guidance onto the selection of an appropriate platform. And one of the appropriate platforms identified here is a Correlator B design based on a SIL 2 microcontroller. We've decided, for reasons that are explained in the book chapter, to opt for this design. The key reasons for doing this are we can implement our sounder software correctly and comfortably. We can be confident that this software will work using the techniques that we've explored during this course. For example, we'll have an internal monitor, an internal predictor, an internal watchdog timer as part of the control software in this design. And we will use this controller based on commands that are received over this CAN link to the main controller module in the IMS. So we receive commands over this CAN link to control the state of the horn, and that will in turn have us control this power switch, which will control the power to the horn unit. In order to meet functional safety requirement 3, and to ensure that we can meet functional safety requirement 3, which means that we don't want to have false alarms, we don't want to have the alarm sounded if the microcontroller fails, we've opted to go for a Correlator B design, which means that we add an additional external watchdog controller to the system and give that watchdog controller access to a second power switch only if both the EWDC and our main sounder MCU indicate that power should be supplied to the horn. Will that power be supplied? So we can be confident that through this hardware and software architecture we will be able to meet the needs of the application. If you follow through the further notes and much more detailed notes that are provided in the book chapter, you'll see the process that can be used to create an initial prototype of this system that's designed to run on a low-cost evaluation board. In this case, we've opted to use an XMC 4500 microcontroller from Infineon as the target platform, and we run through in the book chapter in much more detail how you can generate the software and determine the software requirements that are needed to achieve what we wish to achieve with this sounder unit. That brings us to the end of this video. Please read Chapter 23 in the ERES2 book before you continue with the course. Thank you for watching.